I would now like to quickly invite Dr. Bill Barber, an IWS specialist and author of a book on thermal hydrolysis process, to share his presentation, please. Dr. Barber.
Thanks very much, Kailash. Good afternoon, everybody. I hope you can see my screen. Just on the share the slide presentation. So as Julia Kopp has just concluded, thermal hydrolysis is one way which you can enhance the dewaterability of primarily waste-activated sludge. So today I'm going to talk about how thermal hydrolysis works and some of the benefits of doing it, and also some of the challenges of thermal hydrolysis. Principally, thermal hydrolysis relates to pressure cooking of sewage sludge. The pressure cooking of sewage sludge is typically around the range of 165 degrees Celsius for perhaps 20 to 30 minutes. These maybe 7 to 8 bar pressure, and these conditions have been found over many years of research since the 1940s. What thermal hydrolysis does is it fundamentally changes the properties of sewage sludge. As we heard before, primary sludge is relatively compressible, easy to water, high fibrous content. Waste-activated sludge is high protein content, high nutrient content. It's highly colloidal. It has a gel matrix. So a lot of work has shown that heating sludge breaks down these proteins, breaks down this gel matrix, releases the quantity of free water in the waste-activated sludge, making it far more easy to dewater and also far more easy to digest. Typically, the viscosity of waste-activated sludge is orders of magnitude higher than primary sludge. So manipulating waste-activated sludge will have huge impacts, positive impacts on downstream management of wastewater treatment. Work has shown that when thermal hydrolysis is used, viscosity drops, but then when a sludge is cooled back down to its starting temperature, viscosity remains lower than an equivalent amount of sludge which had been thermally hydrolyzed. And this is due to the denaturing of the proteins and the physical breakdown of the material. So if we have a closer look at the time frame of thermal hydrolysis, let's say it uses steam to destroy sludge, activated sludge. First mention of this is 1926. There was a patent for destroying cellulosic material using steam explosion. But then looking at thermal hydrolysis, looking at steam injection into sludge, it was really about dewatering prior to incineration. There was the Porteous process and the Zimpro process, which were looked at from the 1940s to early 70s. If you look at the literature at that time, it was all about dewatering. And then in 1973, there was the oil crisis, and there was a lot of emphasis after that point to look at alternative avenues for renewable energy. So a lot of the research shifted at that point to let's try and find more ways to generate biogas, and not just from sludge, but from other materials as well. And then from 1995, there was the first commercial scale operation thermal hydrolysis plant by HIAS in Hamar in Norway, which was installed to protect eutrophication, pollution issues in Lake Mjøsa in Norway. And Chertsey was the first plant in the UK. This is a significant plant here because initially this plant didn't work very well. Thames Water, who installed the plant, regretted installing thermal hydrolysis at that time. They didn't think it worked properly. So there was a few years, the lean years, where not much was going on with thermal hydrolysis. But those teething problems, if you will, were addressed. Subsequently, they have 8 facilities now. So the important Chertsey, I cannot underestimate the importance of the lessons learned in the field at Chertsey, without which we wouldn't be having this discussion today. Subsequently, there have been newer configurations which could be topic for further presentation from around 2010 onwards. So I talked about pressure cooking, but really it's multiple stages. So normally what you'll see is for all vendors of this technology is some kind of pre-dewatering prior to the thermal hydrolysis. The reason being the energy balance, that the higher the dry solids, the lower the energy I need to heat up the sludge to the temperatures I require. Even at 20% dry solids, over 90% of the energy I need is to heat up the water and not the sludge itself. Typically, you want the dry solids to be as high as possible, but not too high. And the reason that you don't want it to be too high is then you start offsetting the energy savings from a higher dry solids against the additional costs of polymer consumption. Obviously, the higher the dry solids, the higher the polymer consumption. And then you have problems with mass heat transfer and handling the sludge if it's very high dry solids. Also, as we've heard in the last presentation, if you have a very high concentration of waste activated sludge, it may not be possible to go even above 20% dry solids, irrespective of the energy balance. So then you have your pressure cooking system. So this is where we will heat the sludge to 165 degrees or so, half an hour. Typically, with respect to dewatering, the temperature, the higher the temperature, the better. So if I heat it to 200 degrees Celsius, the dewatering will be further enhanced. However, the biogas production may fall. And the reason for this is as temperatures increase, you start to release polymers, extracellular material. You start to release these extracellular material, polysaccharides, higher molecular weight proteins. These interact with each other and make refractory colored compounds at higher temperatures. So if you went to much higher temperature, as did with the Porteous or Zimpro process, you generate a liquid which has very poor biodegradability. So there's an optimal temperature range there. Then you provide your heat. This is typically from steam in many systems, but it can be through heat exchangers. So now you have hot sludge. Now you have to cool it down. This cooling water does two things. One, it drops the temperature of the heated thermally hydrolyzed sludge, but more importantly, it controls the chemistry in the digester. So now your digestion loading rate is not related to the viscosity of the sludge as it is typically, but it's related to the ammonia chemistry. So you have to water down the material to make sure the ammonium and ultimately free ammonia is below a certain threshold value, which would cause inhibition in the digester. And then any further cooling then is taken on by specific coolers there. So we showed this video of what happens when you heat sludge at different dry solids. So this is normally what would go into the thermal hydrolysis, around about 18%. And this is what comes out afterwards. So you can see it's a lot more like water. And a lot of testing has shown you can measure how much more like water it is. And you see the dewatering of the biosolids cake, in this instance, up to 35%. For most projects with thermal hydrolysis, it goes to land application. However, having said that, there are many thermal hydrolysis plants before dryers and incinerators as well. So if we look at the growth curve of thermal hydrolysis units around the world, as I mentioned, the first plant was in Norway in 1995. And you see there in 1998 was this plant that was mentioned by Dr. Kopp and myself already in Chertsey, around about 2000. And as I mentioned, there were teething problems with that plant. So between 2000 and 2005, you can see here, not much was really going on in terms of installations. And then around about this period of time, 2006-07, the teething problems were overcome, and there were incentives in the UK for renewable energy generation. So a lot of UK industries, UK water utilities started installing thermal hydrolysis plants in this period of time here. This led to larger facilities, one in Davyhulme in the UK of over 300 tons per day. And then that led on to bigger plants in the United States and also in China. If we look globally at where the interest lies, traditionally it's been in Europe and in the UK. So the UK, relatively small population, but 1 in 5 plants with thermal hydrolysis is in the UK. Approximately half of the sludge produced in the UK is thermally hydrolyzed. There's a growing interest in North America currently. There's less interest at the moment in Central and South America, Australia, New Zealand. but it's growing there. We see many plants in Asia as well. What I've done here with the two pie charts is show that the major players in terms of capacity and tons of dry solids per day are installed. So the light blue there is Canby. See, the second biggest there is Shanghai Pulan, the many Chinese suppliers in terms of capacity. And then the rest, I put the top 5 for each category. So on the right-hand side, we see by number of installations. And then I've just lumped the other suppliers in the green there. So you see there, in summary, there's about 130 of these installations by various suppliers across 5 continents, treating about almost 3.5 million dry tons of solids annually. So if we look at just some photographs of what these pressure cooking systems look like, a lot of them are modular systems. So you see a plant here. This is treating up to 25 dry tons per day of sludge. This one here can treat up to about 90 dry tons per day. Another one of 90 dry tons. This one is slightly larger. So, you know, the range in sizes are from 10 tons per day in terms of installations to over 400 tons per day. So if we take a look at high level mass balance, this is based on the Canby system as a market leader. As I mentioned before, there's multiple stages. One is the dewatering here, where we are thickening the material up. Then we pressure cook it. Then we have our digestion plant and a dewatering. Most configurations are in this way. There are other configurations where the thermal hydrolysis or pressure cooking is done only on the waste activated sludge. There are benefits for doing that if you thicken them separately. And also there are configurations where the pressure cooking is downstream of the dewatering, so it'd be at this stage down here. They could be their topics of future presentations. So if I do a very high level, just if I had 1 ton of dry solids going into this system, I need a little bit less than a ton of steam and roughly about 400 or so cubic meters per ton of dry solids. This depends very much on the type of quantity of the sludge. So as Professor Coppers mentioned, you know, the decisions we make in wastewater treatment have a fundamental impact on the sludge side. So the more primary sludge I have, the higher that number is. The more waste activated sludge I have, the lower that number is. So for comparison, if I don't have thermal hydrolysis, the biogas production will be somewhere from about 285 to 320 or so cubic meters. And then coming out here, for every 1 ton of dry solids I put in and I digest, I'll get roughly 1.6 wet tons of cake material coming out as a biosolids. Again, for comparison, for digestion, I would have probably about 2.5 or wet tons coming out, so or 2.7. So I've got at least a third to 60% as a reduction in the volume. We look at the energy balance. A lot of questions about the energy that you need to provide for steam. What I've done here is calculate typical energy calorific value based on a 75% dry, 75% volatile solid in the cake. Gives me a little bit over 5,000 kilowatt hours of energy in the sludge. With thermal hydrolysis, I can extract biogas with just under 3 megawatt hours of energy. In comparison, I need 760 kilowatt hours typically for the thermal hydrolysis, and that's roughly 25% of the gas. However, most plants have installed cogeneration. So from that 2,900 kilowatt hours, I can generate approximately 1 megawatt hour of electricity. And I have high-grade heat, which I can recover to accommodate that 760 kilowatt hours. That number is around about 650 kilowatt hours. It still needs a small parasitic load, which is about 1 to 3% of the biogas. And the cake coming out still has a high energy content, just over 2,000 kilowatt hours. So depending on the type of sludge, I can get anywhere from about 15 to 20% more biogas. If I have only waste activated sludge and no primary sludge, I can see maybe 50% more biogas. So the more primary sludge, the greater the benefits of thermal hydrolysis. So I can see more biogas, but then I need some energy to make that system work. So if I was thinking about installing thermal hydrolysis only because of biogas production, I would suggest that it's not necessarily a driver by itself for thermal hydrolysis. There are easier ways to get more biogas if that is the driver. Having said that, there are many reasons why you would put thermal hydrolysis in. I'm going to talk a couple of those now. There's a bunch of reasons here. As we mentioned, the topic of this presentation is dewatering. And it's a well-known fact that heating sludge at certain temperatures fundamentally impacts on dewaterability. This work here is a paper from 1951. As I mentioned, most of the early work in thermal hydrolysis was for dewatering improvement. In this instance, this was on raw sludge. I don't know if you could see the detail, but it says half an hour at 360 Fahrenheit. This is half an hour at 165 degrees Celsius. And they saw massive improvements in dewaterability. When thermal hydrolysis was applied to raw sludge without digestion, the dewaterability was typically between 50 and 60 percentage points of dry solids. So ironically, putting a digestion plant makes the dewaterability worse because a lot of the extracellular material that you destroyed by heating is then partially reintroduced due to biological action in the digester. So as a rule of thumb, we saw Dr. Kopp's numbers before. Full-scale facilities have seen anywhere from roughly 7 to 10 percentage points if the thermal hydrolysis is installed upstream of digestion. But as I mentioned before, there's this configuration where it can be installed downstream as a dewatering aid. And there, the dewatering is typically, rule of thumb, twice as good as it would be if it wasn't there. So for example, if I have a normal digestion plant, dewatering sludge to, let's say, 25%, if I put thermal hydrolysis downstream of that plant, I'll be dewatering to roughly 50% dry solids. So this is very, very good, especially if you've got thermal systems that rely on the amount of water in the sludge, such as dryers or incinerators. They'll have a huge impact on the energy balance of those kind of devices. Another reason why you want to do thermal hydrolysis is loading rate in the digester. So if we look at typical biogas production, you see a typical monokinetics kind of curve you see here, where you see the increase in biogas production with time is this part here, this early part, that is limited by the hydrolysis rate, and the part that levels out is the extent of biogas production limited by the thermodynamics. So if I have endless amount of biogas, endless amount of retention time, I don't need any pre-treatment system. So what thermal hydrolysis and other hydrolysis systems do is manipulate the sludge to prevent hydrolysis from being a limiting step. So what that means is I get this something that looks more closely to this light blue curve. So I get more biogas in a shorter period of time. I don't get more biogas if I have endless retention time because this is fixed by stoichiometry. But when I bring in the retention time as a variable, then that makes a big difference. So typically for a mixed sludge, I may see 20% more biogas if I'm designing my digesters for 20 days retention time. However, a lot of designs of digesters are based on textbook numbers which were written in days before thermal hydrolysis and other pre-treatments were available. So a lot of the designs are sort of very conservative by default. If I look at, say, 10 days retention time, I'll see roughly 50% more biogas with thermal hydrolysis than I will in its absence. And if I increase the retention time for thermal hydrolysis from 10 to 20 days, and I look at this light blue curve here, I may only see another 5% more biogas. So the question becomes one of economics. Is doubling the size of the digestion plant worth 5% more biogas? And that depends on on where you are in the world and the cost of construction and other variables. So really, so putting all that together as a rule of thumb, I would say for standard digestion, you typically need anywhere from 320 to 400 meters cubed of digestion capacity for every ton of dry solids that you put into that digester. To compare with thermal hydrolysis, you need roughly 100 to 140 cubic meters of digestion capacity. So I'm getting more biogas in less retention time. And because the viscosity is much lower, I can double the concentration. So instead of having 5% dry solids at 20 days, I could be digesting 10% solids at 10 days. Now the limitation becomes one of washout of the bacteria, not due to viscosity or hydrolysis. Interestingly, a lot of studies have shown when you look at the microbiome of these digesters, there are very few organisms capable of hydrolysis in the microbiome of a thermal hydrolysis digester because those organisms are not required anymore. Another reason is the quality of the biosolids. So I've got a picture. This is at Blue Plains works I took earlier before the virus took over. This was early in the year. There's been a lot of work in the US, WEF, looking at something that they looked at in terms of regrowth, odors, and sudden increase. So they called it ROSI. A lot of people were finding that with Class A systems, systems which were supposed to be Class A, so that's enhanced treated 6-log pathogen kill, which means you have much wider options for recycling of that material. They found that they were measuring pathogenic marker organisms which were in excess of the requirements of Class A, especially after dewatering, especially with a centrifuge. So theory went that if you have a high shear centrifuge, you're breaking flocks apart, releasing some of the substrate and releasing bacterial growth and also odors. There was a very strong link between the regrowth potential and odor potential. And you can see here they tested a wide variety of pre-treatments such as enzymic hydrolysis, which is essentially another way of saying biological hydrolysis. They looked at 70 degrees C liquid pasteurization, thermophilic digestion and temperature-phase digestion, and thermal hydrolysis. And they found that it was more prevalent on a centrifuge than a belt press because you didn't have the shear on the belt. But they found that thermal hydrolysis-based systems were independent of belt or centrifuge dewatering, and they never had an issue. The other plant that never had an issue was this one here, this 4-stage thermophilic anaerobic digestion plant, which is in Canada. And that was a plant running at 25 days, 4-stage series digestion. This is another study that complements the previous study. So this one looks at all of Class A systems, but with respect to their odor potentials. They are measuring mean detection threshold, which is you take a sample of the sludge and then you dilute it and see if you can still smell it, and you keep diluting it until you can't smell it anymore. So the more dilutions you have, the stronger the odor. And they found that with the red and the dark orange here were mainly anaerobic digestion, some form of advanced digestion such as thermophilic digestion or temperature-based digestion, but also drying systems. So thermal drying systems cause very odorous materials. The two thermal hydrolysis samples were taken. It's these two here, 21A and 13A. 18A was a sample of composted material which had been sat around for 3 months and had stuff added to it. The other samples here are like aerobic ATAD systems and other digestion systems. So the point of this graph here is there are many Class A systems, but not all Class A biosolids are the same. Lower carbon footprint. This is another reason you may consider doing thermal hydrolysis. So a lot of the benefits of thermal hydrolysis have an impact on carbon. So for example, I can get a higher loading rate in my digester because I've changed the rheological properties. That means I have less embodied carbon when I'm constructing a new digestion plant because I have fewer digesters, I have smaller digesters, less footprint. But more importantly, in terms of carbon, I gain capacity in an existing digestion plant. So what I can do here is I can use that capacity that I've increased for digestion of organic wastes. So these organic wastes, every ton of organic material that goes into a landfill generates a carbon footprint of 0.74 tons of carbon footprint. So if I can divert that into a digester and create biogas from that, then there's a huge benefit for the environment. I have better digestion performance, which means I'm generating more renewable energy. It also means less biosolids are coming out of the digester, so I have less transport of that material and less processing. As you mentioned earlier, Dr. Kopp, I have better dewaterability, which means I have less water in that material, which means if I have a dry or an incinerator, the energy balance is lower. I'm burning less material, drying less, which means the carbon footprint is less. I have less biosolids, so I'm transporting less material. And I have a better quality of product. So this opens up new land bank opportunities. So I have less material and I may not need to travel as far. So basically, when you look at all these things together, irrespective of the outlet of the biosolids, whether you're going to land application or burning or even going into a landfill, some form of thermal hydrolysis with anaerobic digestion will always reduce your operating carbon footprint. And here's a bunch of studies which have looked at around the world, which have come to those conclusions. But with every success story, there are challenges. So I'm not going to say it's without fault. And there's a number of challenges with thermal hydrolysis, one of which is the economics. The economics may or may not be favorable for thermal hydrolysis, depending on site-specific drivers and the amount of infrastructure that is required. So typically, if I have a lot of infrastructure, either I can reuse or repurpose, I have existing digestion plants, then it becomes more favorable. Also, depending on geographical region, if the building digestion capacity is expensive, then it becomes more favorable. So really, there are three major costs that make thermal hydrolysis viable or not. One is the value given to renewable energy. So the higher that number is, the better it is for thermal hydrolysis. The second is the cost of constructing digestion. So the higher that is, the more preferable it is. And the third major cost is the cost of recycling or doing something with your biosol. The other one is the perceived complexity. I've showed a lot of photographs of what looks like quite complicated equipment. You have pressure vessels and all these things. The reality is a lot of these systems are fully automated. When you see people on sites, people who have visited these sites, people moving around doing stuff are mainly taking samples. A lot of these are fully automatic and don't really need any additional staff members. So, but it does give this perceived complexity. Another one is the energy balance. As I've shown, even if you recover energy as high-grade heat from cogeneration, you still have a parasitic energy load. Depending on the drivers, there are different configurations of thermal hydrolysis which can have a positive impact on this energy balance and even take that parasitic load away. Some people are concerned about steam operation. In terms of wastewater treatment, the steam may seem quite high temperature and pressure, but if you look at something like the oil and gas industry, that is a very low temperature and pressure that we're dealing with. But there is this perception you may have to have staff which are trained in steam operations. A big one here is the treatment of the dewatering liquors. So we talked about dewatering earlier today, but the treatment of the liquors must not be overlooked. By default, anything which enhances the volatile solids destruction of sludge, and when it's digested, is going to, by default, increase the amount of nutrients, because with the VS destruction, you release the nutrient. These nutrients need to be treated, and there's a cost associated with this treatment. And these costs can be significant, can be a third of the whole operating costs of thermal hydrolysis can be to deal with the liquors. And sometimes these liquors have exotic materials in them. So, this is a manageable thing, but you need to be aware of this. And the other one is microcontaminants. So, again, not just with thermal hydrolysis and digestion, but digestion typically, a lot of microcontaminants may pass straight through them. There's been a lot of work with thermal hydrolysis looking at pharmaceutical waste where it has had a huge impact, but things like perfluorinated chemicals such as PFOS, PFAR, these are really need high temperatures to destroy. We're talking about 1100 degrees Celsius. So the temperatures we're dealing with thermal hydrolysis are nowhere near those required. So, you know, it might be part of a solution, but you may need some kind of thermal treatment as well for these microcontaminants. So that really depends on what your requirements are. So to summarize, I'd say using thermal hydrolysis to improve dewatering biosolids management. Just to reiterate, thermal hydrolysis, although you know it's mainly seen as something that improves digestion performance, it was originally used as a dewatering aid for many years prior to incineration. However, you know, in those days it made a material that was quite odorous because of these liquors, and these liquors that were produced were very poorly biodegradable because of the high temperatures that we used. There are many benefits of thermal hydrolysis I've just highlighted, but I wouldn't say if energy generation by itself is a sufficient driver. As I said, if you're looking only at gas production, there are other ways to increase gas production. But typically, you know, looking at gas production in isolation is not a robust biosolids management strategy. You know, there are lots of things about minimizing risk. And there are challenges, as with everything, but these are largely manageable challenges. You can design for these challenges. The digesters may need to be designed differently, but these are all manageable, and these are site-specific. So I'd like to finish with that and refer you to a book that IWA have recently published that goes through a lot of this stuff in far more detail than I've presented here. I'd like to thank you for your time. Thank you very much.
Thank you, Dr. Barber, for this presentation.